So I want to pick it up where we left off at that place. So we're talking about kinetic friction. Who remembers what kinetic friction is? All right, so it's friction that opposes motion. Between two objects or two surfaces that are moving relative to one another. All right, so it's very, very similar to static friction. Now we're just introducing the idea that the two surfaces are actually in motion. If you wrote down an equation that you wanted to, so that you could figure out the magnitude of kinetic friction, it looks like this, not S. Mu sub k times the normal force, right? So an equation that is very similar to that for static friction. We just swap out an S for a k right here in our coefficient of kinetic friction. All right. We talked about this last week. I showed a nice little plot showing how kinetic friction and static friction relate to a force applied. Let's do an example. All right, so we're going to go back and do another inclined plane example. So we'll just do a very simple box. It's on an inclined plane. And I want, if given the coefficient of kinetic friction, hold on one second. I'm trying to figure out what I was thinking here. So, all right, if I gave you, I wrote down a bad example. I'm now wanting to change the example that I wrote down. All right, what I actually want this to be is if the plane is at 40 degrees above horizontal, I want to know how fast does the box accelerate. All right, we're going to do that one. And just because, I guess it doesn't really matter, we're going to do this just using symbols instead of using numbers. So that 40 degrees doesn't matter. We'll just call that theta. So let's do this using symbols. That. Nope. I know I'm getting there. There we go. All right, so 40 degrees, we're just going to call this theta, like so. All right, so let's draw a picture. You've seen the inclined plane before. All right, that is a big plane. There's the box. This is theta. It's a very small theta. All right, like so. And I just want to know how fast the box accelerates, given that there's some kinetic friction in this picture, and that's it. All right. So you've seen a free body diagram for this picture before, because we only have three forces. We have the force due to gravity pointing straight down. We have a normal force out this way, and we have some friction back like so. All right, so we've seen this picture before a couple times. We might have labeled the forces differently, but three forces on an inclined plane look very similar. All right, so the first question I want to ask is, how do you think we should orient our axis, our xy axis? All right, so I'm seeing that we should rotate our axis. Why would you do that? All right, so right now if we use our normal axis, which is straight up and down and left and right, we would have to break these two vectors up into their x and y components. If we rotate it so that we are aligned like so, now we only have to break a single vector up into its components, this f sub g. Okay? In addition to that, so I'm just going to draw my full axis there. In addition to that, if I illustrate, what direction is this thing going to accelerate in? All right, down the plane, right? Pretty obvious. So it's going to accelerate this way. So in addition to that, now our acceleration vector only lies in the x direction. There is no acceleration in the y direction. So we get an added simplification because of that. So this is our new coordinate system. I'm going to label this x. I'm going to label this y. All right, and now we've got everything drawn, we can start to solve Newton's second law. So I'm going to start in the y direction. So I'm going to do some of the forces in the y direction. So I just need to add up my forces. In the positive y direction up here, I've got the normal force, F sub n. In the negative y direction, I have gravity, so minus gravity. And I need the y component of gravity, so I need to break that guy up. Let's do it in gray. So I'm going to draw a triangle like this, where this side is fg sub y, and this side is fg sub x. Okay? This angle right here is theta. I know that because I'm looking at, I go from my original x-axis, I rotate by theta to get to my new x-axis, and I rotate in the clockwise direction. So if I start from my original y-axis and rotate clockwise, I will get to my new y-axis. Right, so that's how I know that's theta.
Sorry,
yeah.
So
please.
if you're rotating counterclockwise, would it be 6 or not 60?
I'm basing this, so it's always based on which direction the slope is facing, right? So this way we have sort of a right-facing slope. So I go from my original to my new axis, which is this slope, and I rotated clockwise to get there. If I had another slope like this, then I'd say, okay, I rotated counterclockwise by theta. And that would apply to my drawing.
Rotating counterclockwise or clockwise?
It's just how I explain it. And I apologize if it's confusing to some of you, because anything could be confusing to anybody. But that's how I explain it. That's how I think about it. Okay. Yeah, I mean, in this case, I would never say that I rotated counterclockwise, because I always start from my original axis and rotate to my new axis. Okay, so it just depends on how the picture is drawn.
Okay, but so counterclockwise and clockwise has nothing to do with it.
Well, I mean, just because I start from this axis, whenever you're talking about angles, you're talking about circles. Right. So counterclockwise or clockwise is a logical way to define a direction, right? It's just in this picture, I always start with my original axis, and then I rotate up in the direction that I want to rotate to get to my new axis. So in this case, it happens to be I rotate up clockwise. If I drawn the picture this way, I would be rotating up counterclockwise. It's just how I explain it, because that's how I think it's the easiest way to figure out the angles. Start from the original axis, rotate to the new axis, and then you know. Okay? Let me get rid of that. Okay, so now I have my angle, and I need to break up gravity into its components. I'm looking for the y component here. That's the side that's adjacent to my angle, so I'm going to use cosine, fg times cosine theta. That's all my forces. That's equal to mass times acceleration in the y direction, which I already know is 0. There is no acceleration in the y direction, so I get a big fat goose egg there. And then I can go ahead and solve this guy for the normal force. It's equal to, I'm in trouble with equal signs today. It's equal to the force of gravity, which is just mass times g, so it's mg cosine theta. All right, so that's the y direction. Now I can go ahead and crank out the x direction. All right, in the x direction, I have two forces once again. to the right, I have gravity, this gray guy down here, the x component of gravity. It's just Fg times sine of theta this time, because I've already used cosine of theta. And then I'm subtracting off the force due to friction in the negative x direction. Those are the only two forces I have acting, and that's going to be equal to mass times acceleration in the x direction. And I know that we're going to be accelerating. That's what I'm after. So if I write these terms down then, force due to gravity is mg times sine of theta, minus force due to kinetic friction in this case, so it's mu sub k times the normal force. That's equal to mass times acceleration in the x direction. And if I keep going another step, I'll just write mg sine theta minus mu sub k f sub n. So the normal force I already solved for in the y direction, so I have this term up here that I could just plug in. So mu sub k times mg cosine theta, that's equal to mass times acceleration in the x direction. All right, and so you notice something here, that I have a mass term in each of these. I have a mass term in each of these three force terms. So I can divide both sides by m, and then the equation's solved. I have acceleration in the x direction, which is what I'm after, is equal to g times sine of theta minus mu sub k times g cosine of theta. All right, so a little bit more complicated expression than we've seen before. All right, but it still makes sense because there's this g in there, which is good. And like we've seen before, mass doesn't actually play a role. Right? Mass cancels out because all of our terms have a mass term in them. So mass doesn't affect the rate at which it slides, which is a little bit counterintuitive. You think if there's friction in play that mass might make a difference. All right. Forget the example. Just forget about the slope and everything. All we've done here is the same thing we've done time and time again. Some of the forces in the y direction, some of the forces in the x direction, you just add them up. If there's an acceleration, you set the net force equal to that acceleration times the mass. If there's not, it's equal to 0. All right. Again, if you can get to this step, this equation, and this equation, I'm very happy. All right. Getting past that is a little bit of math, but that's where the physics ends. This is where the physics stops. All right. So being able to draw the picture, being able to rotate the coordinate axis if you need to, that's tricky. And then writing things down, that's where the physics ends, and then the rest is plugging and chugging. Okay, questions about this example? Yeah?
For the angle, so what I see myself on a test doing is marking theta as not where it is right now, but in the opposite finger.
This side? Or this side? Well, this side would be the same thing.
Yeah.
Okay, well, first, don't do that. So every problem we've done with an inclined plane, you may have noticed by now, it's always this angle right here. So it always starts from the block and goes down and to the side or whatever. It's always the angle between the original axis and the new axis. So figure out which angle that is. That's probably theta. Okay? That's why I keep saying I rotate from the original axis to the new axis. The original axis was straight down. The new axis is sort of off to the left here. So find the angle that connects the original and the new axes. And that'll be theta. Does that make sense? That's a little bit simpler than how I've been saying it. Yeah, it's not this one. It's always going to be this guy. I say it all complicated like because I'm trying to get you to think like that, because it could be a completely different example where you have to think along the same lines, and maybe that's, yeah.
So when you're setting up your sum of force in the y and the sum of force in the x, it really means like not your new axes.
It does. So. Yeah, I mean, so this is some of the forces in the y direction, which is this direction right here.
Yeah. Okay.
All right, so the normal force I didn't have to break up into components. Why? Because it lies along the y-axis.
Okay. And then
minus this guy, which is gravity, broken up into these weird angled components.
Okay,
Right,
so
it's
that's
X and Y.
really the FGY right there?
This is FGY right here.
Which is FG cosine theta?
Yep,
That is equal to?
that's exactly right. Yeah.
You would need to give us the kinetic coefficient, or the...
Yeah, if I wanted you to solve this problem, in this case, you know, I would give you mu sub k, I would give you theta. Okay? A lot of the times you'll see problems like this, and you know, I'm going through these examples because these are popular on both, you know, quizzes, homeworks, exams, as well as if you happen to want to take like the MCAT someday. You'll get a problem like this, and you'll only be given theta and mu sub k, and you'll be like, I need mass. You're cheating me. I need mass. But you see, I don't need mass. Right? Mass doesn't play a role here. So a lot of these examples are like that. Anything else? All right, let's do it. Let's move on. So that's all about friction. That's all we're going to do talking about friction. Friction is just a force. All of these things are just forces. Yeah, maybe they have an equation like mu sub k times the normal force, but it's still just a force. All right, so don't treat it for anything more than it is. And we're going to go through a couple more just forces here as we close out the chapter. So the next one that we're going to talk about, we've actually already talked about a little bit, and that is tension. All right. Now, we've met tension a little bit, and the reason I break it up separately is because there's a couple tricks that you need to know, or a couple assumptions that we make when we're dealing with tension. But let me just write it down. Tension is just a force that basically transmits, or a force that is transmitted through a rope or a cord or a string. Etc. But a couple of things to note about tension, at least as we treat tension in this course and most physics courses. We consider these ropes, cords, strings to be perfect. And I'll explain what perfect are. All right, ropes, cords, I'm just saying ropes, but I mean all of the things. What that means is that they don't change. They don't change size or length. And they exert the same force throughout. Which is just a fancy way of saying that they don't stretch. And also a fancy way of saying that they are massless. Right, so we don't consider the mass of the ropes when we deal with tension in this class. Right, sometimes we do, but not here. Okay, so that's the important thing to note about tension. You've already met tension, but we haven't really talked about the details. So let's take a look at what that means in an example. All right, let's do a simple example and then maybe something slightly more complicated. So here's a tree, and I tie a rope to the tree, like so, and then at the other end of the rope, I'm pulling on it. I'm not actually, apparently not touching the rope. Not that it matters. All right, so I'm pulling the rope, and I'm pulling the rope with some force F, very general. Okay, all that I'm doing, all that the rope is doing here, is transmitting my force F that I'm applying to the rope down here to the tree. So if I look at the tree, that force F is being applied to the tree. I'm applying the force F to the rope. That rope is just an extension of my arms. It's pulling on the tree with the exact same magnitude. All right, we're not changing the force at all, nothing tricky. It's just transmitting the force. If I took like a cut out of this rope at any section in that rope, the tension would be F. It would be the exact same thing no matter where I look in the rope. All right, it's just transmitting the force down to the tree. All right. Now, we don't consider ropes with masses or anything like that, but how might that make things a little bit different in this picture? Let's just, for 1 second, let's just pretend that we cared about the mass of this rope. How do you think it might change things? It's a little bit confusing in this picture. Maybe a better picture is if I hang the rope from a branch. So here's the rope. I'm pulling on the rope downwards with force F. And the question is, well, what is the force on the tree? All right, in the massless world, the force on the tree is F. If the rope has a mass, though, what do you think the force on the tree is?
Force of your pull plus the force of gravity.
Plus mg. Exactly. So we just need to include in the mass, then the rope has gravity. It has a gravitational force acting on it. So that's also being transmitted to the tree. All right, so that's the real world. But most of the time, the ropes that we're dealing with are light compared to the forces that are applied. So we sort of ignore that. And it's just transmitting the force. Okay, so we're going to keep it simple. All right, so let's do an example. I'm going to draw some more trees. I like to draw trees. Okay, so has anybody ever heard of an activity called slacklining? Slacklining? Kind of like tightrope. Not quite the same, but very similar. So tightrope is tight. Slackline is, there's a bit of slack in it. So we're going to do the slacklining example. As a rock climber, I do like to slackline quite a bit. I don't do it so much anymore, but once upon a time. So slacklining is just this: you put a piece of webbing, 1-inch webbing, which is about yay big, between two objects such as trees. You tighten it up, but not so tight that it doesn't move, and then you balance on it like you would on a tightrope. The difference being that the slackline can actually move and flex and bounce a little bit, whereas the tightrope is pretty much just taut. Okay, so that's what we're looking at here. Now, has anybody seen 1-inch webbing before? It's probably not. Sometimes if you have like straps, tie downs for your, like you're tying something down in the bed of a truck, they use 1-inch webbing. It may not be the real stuff though. It might be just cheap 1-inch webbing. But it's nylon webbing. It's flexible. It's very, very light. Does not seem to be very strong. So the question here is, what I want to know is what is the tension in the slack line? All right, so what is the tension in the slack line? I need to give you some information. What am I going to give you? I'm going to give you the mass of the person is equal to, let's go with 80 kilograms. And we're going to say that the person standing right in the middle, which means that angle and this angle, these two angles are the same. All right? And those angles, theta, will make them 10 degrees. That looks like a clock. Good Lord. 10 degrees. Okay. So this is a Newton's second law problem, just involving tension this time. So let's go ahead and we need to draw the forces. Gravity seems to always apply. So we have gravity. And then we have tension going off in either direction. That's kind of confusing to look at. When I look at this picture, I think it's slightly confusing, right? Because, tension isn't, like, you're not connected to the rope. So is tension really applying to the person? It's certainly supporting the person. So we're going to draw the free body diagram like this. But it's not like it's pulling the person's legs off. You know, it's not attached, but it is supporting the person. But sometimes people get a little bit confused because you're like, wait a second, how is tension applying to the, you know, supporting the person that's not connected? So you could also imagine we're just looking at a chunk of the, you know, chunk of the cord if you wanted to. We're just looking at a little chunk in the middle. But this is the free body diagram. The slack line is supporting the person, which, you know, the only force acting on, the only other force in the picture is gravity. All right, so in this case, we don't need to rotate the coordinate axis at all. It wouldn't really make sense to do so because we'd always have to break up two different forces because we don't have anything that's perpendicular. There's no acceleration here. The person's just being supported by the slack line. So we're going to do a Newton's second law for the person, and we're going to have a summation of the forces in the y direction. I should draw my axis, I guess. That would help. There's the y-axis. This is the x-axis. So in the y direction, I have gravity pointing down and two tensions pointing up. But I need the y component of the tension, which are these little bits here. So this is t sub y. This is, right there is t sub y. Okay? The tensions, the magnitude of the tension vector is the same on each part of the rope, so I just have two ty's. Those aren't different. They're going to be the same. So what I have then is 2 times ty minus the force of gravity is equal to mass times acceleration in the y direction, which is 0. All right? So twice the y component of tension minus gravity equals 0. Now, if I need to resolve this into its the tension in its y component, because what I'm after here is t, not ty. I don't care about ty. I care about just capital T. So I could do this a couple ways. I could write this in terms of sines, or it would be a cosine if I wanted to. Let's just do that. 2 times t, right, times the sine of theta. Since theta is the same and t is the same, then that's fine. And that's equal to the force of gravity, which I guess I should write as mass of the person times g. So tension then is just equal to the mass of the person times g divided by 2 sine theta. The way that I've drawn this, I was a little bit tricky, and I sort of mentioned it. We're really sort of looking at, a chunk of the webbing. We're looking at like the point of the webbing where the person's touching. And so I've skipped some steps here. You're absolutely right. There's a normal force and there's a gravity, all right? So if I include the normal force, then I sort of get rid of this tension. And then I'm just comparing the normal force to gravity. So I'd have to solve for the normal force. And that normal force, in order to get that, I'd have to solve for the webbing. All right, so I'm being a little bit sneaky here. The real picture is, okay, the only force is acting on the person. I sort of alluded to this. But if I just drew the person, it's a normal force. Oh, no, I do Fn. And then gravity. This is the picture for the person. Okay, and then you'd say, okay, well, I need to know the normal force. That's balancing gravity, but what I'm after is tension. So what I have to do is look at a little bit of the webbing. And the webbing has tension, tension, and then the normal force. So here's the real picture. There's 2 different objects that we have to look at. All right, so if I want to be extremely thorough, and we're going to get to this where there's connected objects, we just haven't gone that way yet. So yeah, I'd start with this picture, solve for the normal force, and then solve this picture for the tension. I sort of cheated and combined them as one. And you'll see that they do this in the book. In chapter 6, you'll notice that sometimes they'll solve a problem, they'll treat objects independently, but you can also combine the objects as long as what you're doing is you're ignoring any forces that are internal to the combined system. So when I combine those two, I can combine the webbing and the person into one, I had to ignore the forces that were internal. I only care about external forces. And the internal forces to the system are the normal force. Right? Those are being applied within the system by the elements of the system on each other. Okay? So it's a little bit more complicated, I think, conceptually to think of it like that. But you were absolutely right. I was sort of cheating by ignoring the normal force. Okay? So this plus this gives you that picture. All right, is that better? Can you see now? And it doesn't look crazy? All right, good. It always helps when you can see what I'm doing. All right, so I've solved for the tension. I know the mass of the person. I know gravity. I know 2, and I know sine. So I can actually get theta here. All right, or I can get, I'm sorry, tension. So if you do that, what you see is that tension is equal to 2257.4 newtons. All right, so 2200 newtons. How does that compare to the weight of the person? So the mass of the person is 80 kilograms. Gravity is roughly 10, so we're talking about a weight of 800 newtons. All right, but the tension is 2257 or 2200 newtons, much, much greater. The reason is because we're being really efficient in supporting this person. We're basically supporting this person with a horizontal line. All right, which is kind of crazy. We have to apply a lot of force in the horizontal direction just to keep the person from falling in the vertical direction. All right, so that's why the force is so large. So that said, a lot of times when I show this to people, I'm like, well, that's a pretty big force, and I didn't bring any webbing, but it's like nylon stuff. It's it's like a belt kind of, a nylon belt. So it's sort of surprising that it can support that much weight. And if you ever go to like a climbing store or REI, you can buy this stuff, and it'll have a load rating on it. Okay, so you can look at how strong the webbing is. Typical 1-inch webbing will support 25 kilonewtons. All right, so add another 0 at the end of that number, and that's about how strong. So about more than 10 times this amount of weight. So it's actually plenty strong to support what we have set up here. So you will deal with problems in your homework and probably on the exam where you have a pulley. The point of a pulley is to redirect a tension force. All right, the key to a pulley, at least in our class, again, we're dealing with idealized massless, frictionless pulleys. All right, we'll never ever not deal with something like that. They do not change the magnitude of the tension. All right, they only change the direction. I'm stating it twice. Ooh. All right, so pulleys don't change the magnitude, only change the direction. So the simplest example that I can think of is this one where you have some mass, and this is a pulley, which then you sling a rope over, and I don't want to do that. I want to put a person on the end. All right, so here's the person pulling down on the pulley. All right, and if we look at this, picture, say we'll give this thing a mass, so it has some force due to gravity acting on it. All right, pulling up on this thing is the force of tension, T. All right, the pulley doesn't change the magnitude, so the tension force is transmitted all the way along this rope to the person. So the question is, how hard does the person have to pull down? So let's say the force due to the person. How hard does that person have to pull down? Equal to the what? So that it doesn't accelerate. So how hard do you have to pull down just to support the weight? So remove the greater than and.
Like just to keep it like above ground.
Just to hold it. Just to hold it there. Okay, so I am going to say it's equal to the tension, and therefore it's equal to the mass or the weight of the box, right? That's what I say. A couple of you said that. If a couple of you said something different, stop doing that. So let's draw the picture and try to make some sense out of this. All right, so remember, now we're starting to get into the land of multiple objects. All right, so mostly up until this point, we've only been looking at a single object per problem. things get a little bit more complicated when you start to have multiple objects. So there's a person, the person is applying the force over here. So what's going on? Well, whenever you have multiple objects, you need to have multiple free body diagrams. So here we have one free body diagram on the block, tension, Fg, right? And then on the person, or the other end of the cable, I guess you could have another one. So we could have, let's just do the person's hand, which we will represent by a small box. Right? It's the force acting on the person's hand, sort of. All right, well, the person is pulling down with the force of a person. What is the other force acting on the hand? The hand is very low in mass, so gravity is negligible. Right, so the person is pulling down. We'll just consider that his hand is the force of the pull. All right, so there's something else going on there. There's a tension force. So what this says, if I actually be very thorough here and I write down Newton's second law for the person, it's not accelerating, right? No motion. So the sum of the force is equal to 0. What this says is tension minus force of the pull is equal to 0. So the force of the pull is equal to the tension. All right, so being extremely thorough. Over here, you probably know what tension is, but I'll be extremely thorough and write it down. I get a similar no acceleration problem. I sum up the forces. I get tension minus the force due to gravity is equal to 0. So tension is equal to the force due to gravity. All right, so now I've got it all. I've got the whole picture here. So if tension is equal to the force due to gravity, all the rope is doing is transmitting that force of tension over to the person. The person is pulling with the same amount of force, with tension. So the force of the person is equal to the force of gravity. Okay? If you stop and think about that for a second, it sort of makes sense. I mean, this is like you go to a well and you pull up a bucket. Right? The tension in the rope, you have to pull, with the amount of force that you have to just hold the bucket. All the pulley is doing is redirecting that force. Okay? Now, of course, if you go to an old well with an old bucket and an old pulley, it might have some friction on there, so you've got some other issues going on. But if it's not accelerating, it's moot. You just have to pull at the force of the bucket, the weight of the bucket. Now, this gets a little bit more confusing as we add in more pulleys. So probably you guys are familiar with the idea that, hey, pulleys can help us sometimes, make things easier to move. So if you add in more pulleys in different arrangements, you can reduce the force at which you have to pull. And we might talk about one of those today, maybe tomorrow, maybe in your homework. I don't know. All right, we're not going to go too crazy with pulleys because it gets complicated when you're doing many free body diagrams. But yeah, the idea of pulleys is you can use them in combination to help make lifting a little bit easier. But in this case, we just have one pulley, so you're not going to get any what's called mechanical advantage out of the problem. Yep.
But doesn't the force that the person is pulling down the rope, doesn't he use less energy? Because he has, since tension is exerted through the rope, doesn't he have to use less energy to compensate?
Tension is what through the rope?
Exerted, transmitted through the rope.
It is transmitted through the rope, but the magnitude isn't changed. So no, you don't have to use less energy. We haven't even talked about energy. So in physics world, definitely not less energy. No, that's okay. I mean, maybe you could make the argument that because he's pulling in a more efficient manner, as opposed to like pulling like this, he's pulling down. You say it's easier, but that's actually making the picture more complicated. All right, so if I said, why is it easier to pull something down than it is to pull something up? Or would you agree with that statement? I mean, it's easier to pull something down, A, because your arms have weight, and so you're letting gravity do some of the work for you. All right, this is a more natural motion than this, so your muscles are better suited for this motion. So things that are more complicated than what we're trying to look at. But in this picture, if I just look at his hands and ignore gravity on his hands and all that sort of thing, that's what Newton's second law says. You only have to pull with the same amount of force as the object weighs. But you don't get any benefit from just having a single pulley. Yeah.
Does the force of tension ever change direction? I thought.
Well, yeah, I mean, so, tension is sort of changing direction. It's not changing direction in this picture, obviously, Why do you keep popping up? All right, so but if you imagine I drew a free body diagram just on like the rope up here, then tension would be applying in two different directions. All right, the next sort of classical problem is to do this, is to draw a table, which then has a pulley, which then is attached to a mass, which is attached to another mass. Mass 1 and mass 2. All right, and so if we make this a problem, which we can do, which I was about to do, so you say that we have a block that has mass equals 4 kilograms and a ball. Sorry, that lower block is actually a ball. Mass equals, I really made the ball heavier, 7 kilograms. And those are connected by a string attached to a pulley. We could even do something like include kinetic friction. So the coefficient of kinetic friction is 0.3. I could ask the question, what is the acceleration? All right, so what is the acceleration of the block and the ball? Oh, I did it. Oh, wait, it's up here. How do I move it? There we go. All right, so I meant to make this a ball. All right, so here we have a pulley, we have a couple masses. All right, now in this case there's tension in this rope, and it's certainly changing direction because up here it's applying to the right, up here it's applying straight up. All right, so now we're changing direction. But we have another problem here, and this is, like I said, it's a pretty classical problem. You'll see that we tend to do a problem like this every time somebody teaches a course like this. It's the sort of basic pulley problem. This thing's going to accelerate. As long as friction isn't too strong, it's going to accelerate. Now, look, this is actually two questions. I want to know, what is the acceleration of the block? What is the acceleration of the ball? Can anybody tell me how those are related? Which one's larger? They're the same, right? Yeah, they're the same. They're attached by a string. So if this one starts to go down, this one's just going to get tugged along at the same rate. Now, of course, this guy is accelerating downwards, and this guy's accelerating to the right. So the directions aren't the same, but the magnitudes are the same. That's what I've written here. So I'm just going to call these accelerations A. Whenever you're dealing with these connected problems, dealing with pulleys, this is usually a very important step, identifying which objects are accelerating at the same rate. Because what I've done here is I've taken two unknowns and turned it into a single unknown, acceleration A. And we'll use that. So the next step then is to start to draw a free body diagram. So let's do the block first. All right, let's cruise through this. I've got tension pulling to the right. I've got friction pulling back to the left. I've got gravity pulling down. I've got a normal force pulling up. I've got all sorts of stuff. All right, that's the picture, 4 forces. Luckily, they're all perpendicular. On top of that, I'm going to be accelerating that way. I like to write it in a different color so I don't confuse it with a force. All right, I'm going to draw my axis like I would normally here. This is x, this is y. So if I write down my Newton's second law, then I have sum of the forces in the y direction is equal to the normal force minus the force due to gravity. That's equal to mass times acceleration, and this is mass 2. Times acceleration A. I've already said that A block is just A, all right? So I'm substituting that in. Otherwise, like I said, I'd have those two unknowns I'd have to deal with. So this is mass times A, not just A block, it's A, all right? Now, another key point here is I sort of am inclined to get the direction right of the acceleration. Oh, that's a 2, yeah, sorry about that. Getting sloppy. All right, now I chose here mass 2 times acceleration. There's no negative sign here, so I've chosen this to be in the positive direction. Oh, God, I'm sorry. I was doing the y direction. My fault. So there is no acceleration in the y direction for the block. I'm jumping ahead. Sorry about that. That's 0. My apologies. So what this says is the normal force then is equal to mass 2 times gravity. All right. Now let's do the x direction. The x direction says that the tension minus the force due to friction, which I could just write as mu sub k times the normal force. The normal force is just mass 2 times gravity. That's equal to mass 2 times A. All right, so I'm starting to skip more and more steps because we're getting further and further along. So tension minus friction, which friction is just mu sub k times the normal force, is equal to mass 2 times acceleration A. I've chosen right to be positive, so I've said the tension is going to be positive and the acceleration is going to be positive. Looking at the picture, I know that's to be the case. But let me say that I don't need to actually get the direction right of the acceleration. If I say that the direction is negative and it is positive, or if I say it's positive and it ends up being negative, it should come out at the end. But the one key, the really, really important thing is that I have to get the direction consistent between these two objects. So by saying that the acceleration is going to be positive to the right of this block, what am I saying about this block? All right, it's going to be negative. It's going to be going down. So I need to make sure that I'm consistent as I work on different objects. That's where sign errors can come in. And if you do that, you can get the wrong numerical value in the end. So you have to be consistent. All right, so I've solved here for the acceleration. The problem is I don't know tension. I know everything else besides tension, so I'm going to need another equation. Luckily, I have another object. So let's move on to the ball. The ball is a bit simpler. I've got tension pointing up and gravity pointing down. Nothing happening in the x direction. So if I sum the forces in the y direction, I see that tension minus mass 1 times gravity is equal to mass 1 times acceleration. And then I stick the negative sign in front because I've already decided that this guy is going to the right, which means that guy must be going down. Again, as long as I'm consistent here, even if I made the wrong choice of the directions, it would come out in the wash because I'd get negative signs where I would get negative signs. Okay? But I just have to be consistent. I have to make sure I put a negative sign there. So if I solve this then for tension, I get tension is equal to mass 1, I'll factor out, G minus A. All right. Now that I have an equation for tension, I can plug it into this equation, and I get a big, sloppy, ugly equation. I get mass 1 G minus A minus mu sub K M2 G is equal to M2 times A. All right, so now I've got kind of an ugly equation, but the good thing here is that I know everything except for acceleration. I should have done this factoring because it's making life a little bit easier. So I'm going to write out this big equation right here. All right, so we're left with M1G minus M1 times A minus mu sub K times M2 times G is equal to M2 times A. Sorry for all the arrows. All right, that's the full equation. Now if I solve for A, I need to get the A's on the right side, so I'm going to do M1 times G minus mu sub K times M2 times G is equal to M2 times A plus M1 times A. This term is actually M2 plus M1 quantity times A. This is all the same. So my acceleration then is just A is equal to mass 1 times gravity minus mu sub K times M2 times gravity divided by the total mass, M2 plus M1. All right, so that's the solution in terms of letters. I didn't even use the numbers. It's more fun. All right, what you notice again here is that there's this gravity term, so it wants to accelerate at gravity. So if you just solve for this ball and it wasn't attached to anything, the acceleration would be gravity. but we're subtracting off this term that's friction. So this sort of seems to make sense, at least as far as each of the terms look. All right, so I'm pretty happy with that, and you could solve for that. If you did plug and chug, you would get something like 5.17 meters per second squared. So if you actually want to check your calculator using ability, I got 5.17 meters per second squared. All right, which is, yes, slower than gravity. So I know it's got to be slower than gravity. All right, so again, this is just a Newton's second law problem. We're adding in the additional complication of connecting different objects. Whenever you start to connect multiple objects, you're going to have to start to do multiple free body diagrams. Right, so it's going to make life a little bit more difficult. But just break them up into individual objects and start simple.